Hi, my name is Manish Gupta, and in this video, I'm going to talk about this new model called as MiniCPM-V, which promises basically a GPT-4V level, accuracy on multimodal tasks, but can fit on your phone. So it's basically highly effective and very, very efficient. It can actually fit on your phone. So let's get started. What is MiniCPM-V series of models? So it basically turns out that they released like multiple models as part of their series, but what is it and where does it fit in the entire scenario, in the entire landscape, right? So just to call out, there have been several multimodal large language models which have come up recently. I mean, in the past 1 or 2 years, starting from Flamingo, Blip 2, Cosmos 1, Cosmos 2, MiniGPT-4, Lava, several of them that are named here. I won't name all of them, but they're all present here, right? Um, Now, they could be large in size, but over time, what has also happened is that people have been trying to come up with smaller and smaller models, so which can be deployed on edge devices, right? For example, the 5 model, Gemma model, mobile LLM, mobile VLM, mini CPM, which is basically what we are going to discuss, the visual version, right? Mini Gemini, Polygemma, and so on. So they are these models which can actually be deployed on edge devices. In fact, this picture on the y-axis, it shows you model size. On the x-axis, it shows you time. So interestingly, this red curve basically seems to say that, yes, I mean, initially people had come up with GPT-4V, which is pretty large in size. In fact, the actual size is unknown, right? The actual size for all of these closed source models is unknown, basically. But then over time, people have been trying to come up with smaller and smaller models, as you can see from this red curve, right? Which basically, so for example, intern VL 1.5 million, 1.5, this particular model essentially is about 26 billion parameter in size and performs really well. So it performs really well. So by the way, on the color basically tells you about the OpenCompass score. OpenCompass is a benchmark of 11. It's a combination of 11 popular multimodal benchmarks. And the red color basically tells you that it performs really well. So of course, GPT-4O performs really, really well. But then intern VL 1.5 is not too bad, right? On the other hand, this blue curve basically, and of course, each of those dots that you see is a different multimodal model, right? Depending on when it came up and what accuracy it provides and what is the model size, right? Now, interestingly, this blue curve actually tells you about the compute power. So essentially, it tells you how the edge device compute power is increasing, right? Over time, of course, people have been trying to fit more and more chips onto smaller and smaller devices, and therefore the compute power is increasing over time. And what you observe is that we are now at a very interesting time point where essentially we have multimodal models which can actually fit on phones, and which is what is the claim of this MiniCPM-V series of models. Okay. It basically says that, yes, we can outperform GPT-4V, Gemini Pro, and Claude 3 on these 11 popular benchmarks, but still can be efficiently deployed on mobile phones while supporting 30 plus languages, low hallucination rates, and also supporting, things like OCR capability on very large, reasonably large 1.8 million, 1.8 million pixel high resolution images. So what can MiniCPM-V model do? I just put in some of those snapshots, which are there also in this paper, to basically explain different kinds of multimodal tasks that one can do using these kinds of models, which can actually fit on a phone. Remember, you can actually now do these kinds of things on your phone. Okay, so you could basically give it a news article of this kind and ask, please identify the text in the picture. So it can actually nicely do all the OCR. In fact, it can do more. So it can actually tell you that this is the title. So this particular part was extracted as a title. It can tell you this is the date, this is the author. It can tell you, well, this is basically it can actually extract the image caption also, by the way, right? And then it can basically tell you this is the body text, word by word, without any mistakes, right? So that's so nice from an image, right? It can also do other interesting tasks, like based on this picture, make a detailed meal plan for me. And this is like a typical diet pyramid from kids' books, right? In that senses, um, it can actually create a very interesting diet plan overall, so as to satisfy all of those levels in the pyramid. Okay. You can basically give it a boarding pass and tell it, hey, please extract all the fields for me. It nicely extracts and gives you as a JSON. You can also tell it to convert something in Markdown format. And remember, you can actually also give instructions in Chinese. It can give you the Markdown formatted table, right? Very convenient and interesting to basically take, these kinds of tables and put them up in Markdown format, right? take these kinds of tables from Excel and PowerPoint and put them in Markdown. Okay. So you can also tell it to explain the code clearly in detail. So it can basically take the image of this code and then tell you, hey, this is what the code means. It can take these paintings and then tell you what this painting, describe the painting, what is the, tell the title, art style, and so on. And of course, it can basically also work for multilingual use cases. So basically, it can take architecture diagrams and give you detailed description of how the system works. It can take images of this kind and tell you what's horribly wrong about the interior in this image, saying that, hey, it has some mismatched furniture style and color scheme is lack of cohesion color scheme, cluttered space, and so on. It can actually take so basically this description, and you can actually ask it, hey, can you list all the items under pancakes? And it can basically tell you, hey, what is all under pancakes? So from the list, it can basically nicely read out things and understand essentially what does under pancakes could mean, right? It can also take an infographic of this kind, and you can basically ask, hey, I want to know the trends and data. So I want to know what are the trends from this data. Analyze this data. It can actually then tell you a very good analysis. This could be very handy if you basically want to have a picture in your paper and you want to sort of write some good analysis on top of it, right? Yeah. So now that we know what all it can do, what is its architecture? So the architecture basically comprises of three main parts. So there's a visual encoder, there's a shared compression layer, and there's an LLM. So of course, it's a multimodal model, so there will be a visual encoder and there will be a LLM, but there's also a compression layer in between. Okay. Now, the interesting part is that, so the visual encoder, I mean, from an architecture perspective, it is a typical SIGLIP SOVIT model. So it's basically a VIT model, some sort of a VIT encoder, right? But then what is really interesting about this encoder is the adaptive visual encoding that they do for the input image before they actually encode it using this VIT model. Okay. So the adaptive visual encoding has two main goals. One, it should respect the raw input aspect ratio. Remember, most of the encoders don't respect this. So they basically say, oh, whatever is the input image, well, let me resize the image into a particular input resolution and size that my VIT model expects and make it work, right? But this one basically wants to respect the raw input aspect ratio and preserve, but at the same time also preserve sufficient details. Okay, so preserving sufficient details basically means having a maybe smaller and smaller crops or other tiles in the image, so that but then at the end of it, if you have smaller tiles in the image and you reserve too many tokens per tile, you end up with too many visual tokens. So therefore the second goal is to ensure that the number of visual tokens is not too many, so that it is affordable to be run on edge devices. Okay, so that's that. So the way the adaptive visual encoding works is that it tries to preserve the aspect ratio. So it takes the input image and then it basically takes the width and the height of this image, right? Height and width of this image, and then tries to understand that, hey, if my VIT model expects certain height and certain width of the image, what is the number of tiles that I would really need to divide this entire image into? Right, so H into W. So that's the overall area of the input image, and this is the area of the image that is expected by the VIT model, right? It tries to get that. And it actually works only up to, this ratio. This ratio, I call it as N. It works up to a ratio of 9, which basically means that it can handle up to about 1.4 million pixels kind of images, right? So for example, in this image, if you ended up with that N is basically about 7, you basically take N plus 1 and minus 1, so essentially 6 to 8. And then what you try to do is to try to divide this image into tiles of this kind, such that when you multiply it, they are either 6, 7, or 8. Okay, so basically you have to divide this image into some sort of number of tiles, number of rows, and number of columns. Okay, and then you pick. So these are all proposed solutions, right? These are all possible partitioning solutions. And then you pick that one, this one. Why? Because the aspect ratio of this guy is the closest matching with the aspect ratio of the original image. Okay, that's how they basically choose the partitioning. And this partitioning is so fancy. I mean, I like it. Okay. Now, after the partitioning is done, basically each of those partitions, of course, gets position embedding. So you have like one-dimensional VIT's position embedding, which are basically transformed into two-dimensional position embedding with some interpolation, so as to make the position embedding work. So that's that. Now, once this position embedding is done, that's the input that goes to your VIT model. VIT model actually also receives the full image. So the full image, and then these are the different partitions or the tiles that are also provided to the VIT encoder. So that's that. Now, further you have this shared compression layer. And what does the compression layer do? Well, it's a perceiver resampler structure. So basically the idea is that, depending on the number of tiles, the input image can be divided into variable number of tokens. Okay. And variable number of tiles, which leads to variable number of tokens from VIT. Okay. So but we don't want too many tokens from VIT, and therefore what they do is to basically boil it down all to 64 queries for MiniCPM V1 and 2, and 96 queries for MiniCPM V2.5, which is based on Llama 3. Okay. So that's what they do. So they basically, of course, there are three variants of MiniCPM in the series, V1, V2, and V2.5. So what they do is to take the overall input coming from this VIT visual encoder and try to compress it down to 64 queries or 96 queries. Okay, the way this is done is using the perceiver IO kind of resampler. And again, that's sort of out of scope for this particular video. I've done that earlier in another video, so you can look at that video. Okay. It uses one layer cross attention. So basically they initialize the architecture with like 64 queries, which are randomly initialized, right? The 64 vectors, and then they basically use cross attention along with these set of vectors so as to get a revised version using just one layer of cross attention, revised version of these 64 vectors, of course, cross attended by the input coming by the output coming from the visual encoder. Okay. So these 64 queries or 96 queries, depending on the version of MiniCPM, are then fed to the LLM, so large language model, for further processing, for basically decoding, right? So essentially, the large language model is going to take these inputs and start decoding. Now, they also have a spatial schema. So the tokens of each slice are separated by a slice, start slice and end slice token. And then, different rows. So there are two rows here. The two rows are separated by a new line token that you see there. Okay. That's that. That's the broadly the architecture. Now, how is it trained? So it's trained in a very rigorous manner in three different stages, three pre-training. So pre-training, supervised fine-tuning, and reinforcement learning with AI feedback in a visual form, right? So pre-training itself actually has three different stages. So I'll describe three pre-training stages here. Stage 1, stage 2, and stage 3 of pre-training, and then you do supervised fine-tuning and RLAIF, right? So stage 1 of pre-training basically trains the compression layer, keeping everything else frozen. So everything else, all of those other modules are just kept frozen, initialized using whatever are the initial model checkpoints, and everything else is frozen. Compression layer is trained, okay, pre-trained. The visual encoder's resolution is set to 224 cross 224 because that's the natural resolution for the VIT model. You randomly select two, and then what is the data on which you train? Of course, you train on image captioning data, English and Chinese image captioning data, which is sourced from several other benchmark data sets. Okay, several other benchmark data sets. So this is the top part is the image captioning data. The bottom part is OCR data. We'll use that for stage 3 pre-training, but stage 1 and 2 pre-training basically use the image captioning data. I mean, of course, this is huge data, so 410 million, 110 million, and so on. But 200 million is sort of sampled, so as to essentially train do the stage 1 pre-training. Stage 2 pre-training is done by increasing the resolution from 224 to cross 224 to 448 for cross 448, right? And rather than training the compression layer, you train the visual encoder. You leave everything else frozen, right? And again, you train on a similar kind of 200 million data sampled again from this large data set. Okay. Stage 3 pre-training basically trains the visual models, which basically use the adaptive, and at this point they use the adaptive visual encoding strategy, right? Which basically means that your resolution now increases significantly, and you can actually handle various kinds of aspect ratios, basically, right? So here, both the compression layer and visual encoder are trained. LLM is kept frozen. So they don't really mess around with the LLM. LLM is kept frozen, but both the compression and the visual encoder layer are further trained, right? Further pre-trained. And of course, it trains not just on image captioning data, but also on the OCR plus knowledge data. Okay. That's that. After all of this is done, they do another phase of supervised fine-tuning, which is basically done using this part 1 and part 2 data, which is sourced from crazy number of benchmarks that you see here. So imagine the kind of effort that is required to be able to use all of this data, right? So part 1 data, comprises of several kinds of image processing tasks, including visual question answering, knowledge-based visual question answering, grounding, visual reasoning, mathematical question answering, OCR, a chat-based task, visual dialogue kind of tasks, and so on. Now, part 2 kind of Of course, super fine-tuning is done in two stages again, right? Part one and part two. So part one is that. Part two basically comprises more of OCR data and instruct fine-tuning data and text-only data as well, right? So that's that. Now, the third part of training the MiniCPM-V model beyond pre-training and supervised fine-tuning is reinforcement learning. And the way reinforcement learning is done is basically what is shown here. It basically in turn comprises of three phases: response generation, feedback collection, and DPO. This is pretty, I mean, it was pretty much a standard reinforcement learning strategy, except for a minor change, which I'll talk about. So typically, of course, they take the current model and call it the policy model. From that policy model, you generate multiple responses given instructions. So the instruction is an image, you generate two responses, for example. Well, typically you generate more responses, just two of them are shown here. For each of the response, you basically ask a Llama 3 8 billion model to divide each response. Each response is very complicated. You divide it into m different atomic claims. Okay, so you take the big response chunk, you divide it into m different claims, and these claims you try to validate them using an LLM. So you basically ask the model, hey, is this claim true or not given the image? Okay. So this LLM model is basically, Omni LLM 12 billion for the V2 version of MiniCPM, and it is Lava next Ye model for MiniCPM Llama 3. Okay. So the idea is that you don't just generate, you just don't depend on the responses. To evaluate the quality of responses, you basically evaluate the quality of the claims made in those responses. And if most of the claims are correct, you basically say, oh, this is a great model. If this is a great response, if most of the claims are wrong, you say this is a bad response. Okay. So that's what you do. And that is what helps you generate preference pairs. So given a response, now you actually have a score indicating how many claims are correct, right? And that score is basically used to, generate preference pairs. So response one, response two kind of preference pairs, where response one is preferred, has more correct claims, and response two is not preferred, has more no kind of claims, right? Has less of yes claims. Okay. So that's the preference data set that you create. And that overall leads to about 6,000 preference pairs, which basically they use to do reinforcement learning with AI feedback and overall train this model. Okay. So lastly, let me talk about how do these MiniCPM visual models perform. Well, they evaluate performance over, again, very rigorously over many benchmarks. So OpenCompass, which itself is basically a collection of 11 different benchmarks comprising of MMMU, Math Vista. MMMU is basically by itself like tens of data sets internally, right? So very rigorous work in that sense. Is Lava Bench, Bench, Math Vista, MME, and so on. They also evaluate performance on real-world QA, which is real-world spatial understanding-based question answering, right? OCR benchmarks, OCR bench, text VQA, doc VQA, and so on. Hallucination benchmarks like object hell bench, right? And so not just that they compare on several data sets that you see here, data sets and benchmarks, you see them here, but they also compare with many models. Some of them are proprietary like Gemini Pro and GPT-4V and Claude 3 Opus, but they also compare with a large number of open source models also, right? And clearly you basically observe that on OpenCompass, for example, MiniCPM scores 65.1, while GPT-4V is 63.5. Okay. I mean, let's not claim that it is better than GPT-4V. Maybe it is better, in fact, on many of these tasks, but great to find that it is actually comparable, right? Even though it is much smaller in size, even though, overall, these models are pretty small in size. Okay. Such that they can actually fit on a mobile phone, right? So the same holds for OCR benchmarks as well. As you can observe, OCR bench, I mean, it basically scores 725, whereas Gemini or GPT-4V scores just 645 and so on, right? So that's that. Now, yeah, I mean, here are more examples. So there is a long article. This is an example to show that MiniCPM Llama 3 V 2.5 model can actually handle extreme aspect ratios as well. So essentially, this is an article which is a very long article, right? Stretching three of these screens, right? And you can actually ask it, describe the content in this picture. It does really well. So it can actually handle images of that kind as well, right? It can basically also avoid hallucinations. So given this kind of an image, you can basically ask two models, MiniCPM or GPT-4V, hey, create a detailed account of the image encompassing visual characteristics, colors, shapes, and so on, right? So MiniCPM basically gives you this kind of a result. Most of this is true. Some of this is partially true in some ways, but GPT-4V, it basically comes up with several hallucinations. There is no clear blue sky. There's no round headlights. Also, the script is not a combination of thrice script and numbers. So a lot of hallucinations in GPT-4V, while hallucinations are typically lower, as can also be observed in this Hellbench dataset or benchmark. Right? Hallucinations typically are lower in MiniCPM compared to MiniCPM visual model compared to the GPT-4V model. Okay, so in summary, in this video, I talked about MiniCPM-V series of models, which are both effective and efficient multimodal large language models. Their architecture comprises of some interesting tweaks, including adaptive visual encoding, multilingual generalization. Although I did not talk about multilingual generalization, they also do supervised fine tuning with multilingual datasets, which gives them multilingual generalization on 30 plus languages. And then an interesting reinforcement learning with AI feedback, visual feedback kind of a system where they basically break down the responses into claims and then try to evaluate the quality of a response based on the quality of the individual claims themselves. Right? Overall, MiniCPM-V series of models achieve GPT-4V level performance with significantly fewer parameters. Okay, so that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.